Hey, what's up guys? This is Dr. Vivek Palipuram bringing you the next lecturette in ECPE 127. Now in this lecturette, I'm going to cover probability density function and expected value of a continuous random variable. The probability density function happens to be the most important probability model for a continuous random variable. It is even more important than the CDF. In fact, we are going to exclusively use the probability density function PDF to calculate all kinds of probabilities with continuous random variables. Now, you should remember the fact from our previous lecture that we will always be interested in finding probabilities of events that take this form. We'll be interested in finding the probability that x is greater than x1, but it is less than x2. Essentially, we'll be interested in finding the probability that x belongs to an interval x1, comma x2. It really doesn't matter whether x1 and x2 are inclusive or exclusive. It doesn't matter because the probability that x takes on either of these two endpoints is actually 0. So we are going to use probability density function to evaluate expressions like this one. In our previous lecture, we had also seen the properties of cumulative distribution function. So the cumulative distribution function for a continuous random variable is going to be continuous, meaning that it is not going to have any discontinuities in it. So let's focus on probability density function. Let's first start off with the definition of what a probability density function is. Probability density function. Now the probability density function PDF is written in math using the small f. So it's the small f of x, which is the d by dx of capital F of x. So probability density function is actually the first derivative of a CDF. Now the PDF is much more interesting than the CDF. When you consider different random variables, the shape of the CDF of those random variables are quite similar, meaning that they are going to start at 0 and eventually they are going to climb up and then they are going to saturate at 1 and they cannot move beyond that. So that's an example of a CDF of one of the random variables. Some other random variable may have a similar shape which moves like this. Some other random variable may have another shape that goes something like that, and some other random variable may have a straight line that shoots right to 1 and then it's stable there onwards. So essentially all of these cumulative distributions have the similar shapes. They go from 0 all the way to 1. They are the increasing function of x. What truly differentiates these CDFs is the rate of change of these individual CDF, right? For example, this CDF right here has a much higher rate of change compared to the CDF, for example. So it's the rate of change of the CDF that is the most important aspect for a continuous random variable, and it is something that differentiates these continuous random variables. And the rate of change of the CDF is the probability density function. There is one more physical interpretation of what the probability density function is, and that physical interpretation is it is an indicator of the probability that x is near small x. That's what it gives you. It gives you an indication of the probability that x is near small x. Always remember, guys, probability that x is equal to small x is always going to be 0 for continuous random variables. What we can do is guesstimate what the probability is that x is near small x. And let's take an example here of a CDF whose shape looks something like this. So if I were to consider a point small x here, the value of the CDF is f of x at x1. If I were to take another point that is delta units away from this, let's call it x plus delta, there the value of the CDF is f of x at x1 plus delta, right? Well, it's x since we are dealing with x. So let me just remove this x1 because it's misleading. So the value of the CDF at x is f of x. The value of the CDF at x plus delta is x plus delta. X plus delta. Now the probability that x is greater than small x but less than x small x plus delta is equal to f of x at x plus delta minus f of x at x. Now I'm going to do some simple math manipulation here, and that is I'll multiply and divide the right hand side with delta. And then if I were to apply a limit that delta is as close to 0 as possible, then something interesting is happening here. If delta tends to 0, then this term right here, or this equation right here, essentially means that x, your random variable capital X, is near small x. That's what it means. Because if this interval were to get shorter and shorter and shorter, then you're essentially interested in finding the probability that x is near small x. And when you apply this limit form, this term right here becomes d by dx of capital F of x. And if you were to replace this delta term with a proportionality constant, then you will have probability that x is near small x to be proportional to d by dx of f of x, or in essentially it is proportional to f of x. So this term is f of x, the probability density function. So that's what probability density function is physically interpreted as. It is an indicator of the probability that capital X is near small x. Remember guys, we will in fact not be interested in finding such probabilities either. We are going to solely focused on finding the probabilities that take this form. What is the probability that x is greater than x1 but less than x2? This is something that we'll always be interested in. And we are going to use probability density function to evaluate this equation or this probability. Okay, so let's move on further. So here's an example of multiple cumulative distribution functions for different families of continuous random variables. So this is the shape of a Gaussian random variable here, which is quite similar to an Erlang random variable's shape. Now the exponential random variable and zip random variable, both of them have quite similar CDF, but it's the rate of change of the CDF that makes them strikingly different. And that's why we focus on PDF, which is d by dx of capital F of x. Okay, now it's not uncommon for us to draw a parallelism between the concepts of discrete random variables and the concepts of continuous random variables. When we discuss discrete random variables, we focus on the probability mass function, which gives you the probability that capital X is equal to small x. For continuous random variables, this item is equal to 0. It is 0 for continuous. It is non-zero for discrete. PDF happens to be similar to PMF, but it is still quite different. Your PDF is going to give you an indication of the probability that x is near small x, and nothing more than that. We will never be interested in what is the value of the PDF at a particular point. No, we are never going to be interested in that. So we are never going to be interested in what is the probability that x is near small x. But as I mentioned before, we'll be interested in finding the probability that x belongs to an interval. So those are the subtle differences between a PDF and a PMF. They are both the probability models of respective discrete and continuous random variables. But there are a lot of difference when you consider them mathematically. Let's go over some theorems associated with the PDF of a continuous random variable. So as PDF is the first derivative of f of capital F of x, if you were to apply the reverse calculus here, you can obtain the CDF by integrating the PDF from negative infinity to x. This is your Calc 2 concept. We are not going to go too much into detail, but we'll just consider them as simple truths or simple truth statements. or simple statements that are true. If you were to integrate a PDF from negative infinity to infinity, that should give you a value that is equal to 1. All right. Now, the most important theorem that you will use in order to find the probabilities of this form is theorem 4.2. It gives you the probability that x is greater than x1 but less than or equal to x2 in terms of integration of the PDF. Essentially, probability that x is greater than x1 but less than or equal to x2 is an integral of small f of x, the PDF, from x1 to x2. Now, this is easy to prove if you were to use your Calc 2 principles. If you have to evaluate this probability using the CDF, you would subtract the CDF values at the endpoints of the interval. So this probability is equal to f of x at x2 minus f of x at x1. Now, each of these CDF terms can be written in terms of integral of the PDF. So this CDF term can be written as an integration of the PDF from negative infinity to x2 using the previous theorem. And this term can be written as integration of the PDF from negative infinity to x1. Now, using Calc 2 principles, you can combine these two integrals into a single one, which goes from x1 to x2. So that's a simple application of Calc 2 principles. We will not be worried too much about how we got to this point because it's a Calc 2 principle, but we'll be very interested in applying this formula to calculate the probabilities. So that's theorem 4.2. Now, let's discuss some do's and don'ts when we use CDF or the PDF of a continuous random variable, because it's easy to fall into one of these traps with respect to their usage. Whenever you have to use the CDF to calculate the probabilities, always subtract the CDF values at the endpoints of the interval. That's the way that you obtain probabilities of these events. If you have to use a PDF instead, you're going to integrate the PDF from x1 to x2. This is how you are going to obtain the probability that x is greater than x1 but less than or equal to x2. Now, sometimes students fall into a trap with respect to usage of CDF and PDF, and this is this one right here. In fact, I have fallen into this trap myself. For example, I was presented a CDF and I was asked to calculate the probability that x was greater than x1 but less than or equal to x2. Now, I did not remember this property of the CDF as to how to evaluate the probabilities using the CDF. So what I ended up doing was I integrated the CDF from x1 to x2 and I got a number which was greater than 1. Now this can never happen. Sometimes it's also tempting to differentiate the PDF in order to calculate the probabilities. Such things happen when you have not reviewed the concepts. So make sure that you are aware of these two concepts so you will never fall into these pitfalls. So never differentiate a PDF either, because the rate of change of a rate of change doesn't mean anything. It doesn't mean anything. Okay, so here's the summary of how you can get the CDF from a PDF and how you can get a PDF from a CDF. If you have to obtain a PDF, you perform the first derivative of the CDF. If you have to get a CDF from the PDF, you integrate the PDF from negative infinity to x. All right. Now, the last concept for this lecturette is the expected values. Now, the expected values for continuous random variable takes a similar form as discrete random variables. Now, if you recall from your discrete random variable lecture, you got the expected value of a discrete random variable in this manner. So summation from negative infinity to infinity, x times the probability model of a discrete random variable. You can easily convert this formula for a continuous random variable by replacing the summation form with integration. X stay the same in both terms, and the probability model now is your probability density function. So this is the formula that is used to evaluate the expected value of a continuous random variable. Now this should evaluate to a constant. So you have to apply your limits appropriately and make sure that this evaluates to a constant. All the theorems that you have seen for expected value in discrete random variables unit still apply. So expected value of x minus mu of x is 0. You can distribute the expected value term and get expected value of ax plus b as a times expected value of x plus b. Variance formula still holds the same, just that the way they are evaluated will be different. For example, expected value of x squared is summation, is integration from negative infinity to infinity x squared times f of x dx, just like how it was summation from negative infinity to infinity x squared times pm of x for discrete case. So all of these moments will evaluate to a constant, and even your variance has to be a constant. And in fact, variance of x has to be positive, because standard deviation is square root of variance. And if you get variance as a negative value, then the standard deviation would be complex, which doesn't happen, which never happens in real life. All right, so I'm going to end this lecture right here, which introduced you to definitions, which included the definition of the probability density function, which is the first derivative of the CDF. We saw how we can calculate the probabilities using a PDF. You just integrate the PDF from the end, and the limits are the endpoints of the interval. So in the next lecturette, I'm going to solve some of these problems and show you how we can use the theories that was introduced in this lecturette to solve some of these problems. All right, guys, adios.